Hi. So today I'll be sharing on linear codes, Calderbank-Shore-Steane codes, and Gilbert-Varshamov bound. In essence, I'll be talking about the paper Good Quantum Error Correcting Codes Exist. But as for the presentation, I'll mainly base it off the relevant chapters of Nielsen and Chuang. Right. This was a paper by Shaw, I think in 1995. Right. So for the overview of this presentation, I'll be giving a bit of background for error correcting codes in general, run through a few examples. Then I'll be talking about linear codes, which is the one that is more relevant to today's presentation. After which I'll be discussing the actual CSS codes themselves. And then I'll give a brief discussion, but I won't prove the Gilbert-Varshamov bound and the quantum version of the Gilbert-Varshamov bound, which is a non-constructive proof that demonstrates the existence of codes with certain parameters, right? So a bit of background towards error correction codes. Why do we have them, or basically what's the deal, right? So the deal is that let's say we have these two people, Alice and Bob, right? Bob asks Alice, "Do you love me?" Right? And Alice has to give Bob a reply. But unfortunately, Alexander Graham Bell hasn't invented the telephone yet, right? So she has to send her reply across a noisy channel, right? So in this channel, we can consider more alphabets, but let's restrict the discussion to just uh binary symmetric channel, which means to say that she just sends over a bunch of zeros and ones, and they can get flipped with some probability to the other one, right? So let's say to say yes to Bob, Alice will say yes. So she will send over a one, right? Unfortunately, with some probability, this one might get flipped to a zero. And as a result, Bob can harbor some ill feelings towards Alice or get unnecessarily disappointed when Alice actually wanted to profess her love. So what will she do? The naive solution is to, or like the one that I guess most of us would come up with, is this thing called a repetition code, right? So what does a repetition code do? I mean, as the name would suggest, you just say it more times, right? So instead of saying just one, maybe Alice will send over 11111, right? And if she's lucky, at most one of the bits will get flipped. But now Bob will see that, okay, Alice sent a majority of ones over. So perhaps she meant to say one, right? I'll just ignore the zero. Maybe it's a glitch in the matrix, right? Literally. But so Bob will just ignore that, right? And as you can see, the more times you repeat for fixed because the noisy channel is a fixed probability of flipping the bits, the higher chance Bob will receive the correct message, right? So here we have seen one of the first solutions, right? To this problem of a noisy channel, right? Which is to add redundancy. And perhaps the whole crux of what we were doing today would be to like cleverly add redundancy, right? Sorry, redundancy, right? So we will, I mean, because obviously you don't want to be ending up to like add. You say one thing, you have to repeat 10,000 times, right? This is like every mother's nightmare, right? Tell the son one instruction, repeat 10,000 times. You want to cleverly repeat it so that Bob will be able to easily decipher if there were any errors that happened. So how does this translate over to sending over a quantum state? Right, which is the problem that we are trying to deal with in this lecture, right? So in this lecture, what's the deal? The deal is that we have this set psi that Alice has, and she wants to send it over to Bob, and hopefully Bob will receive the same state, right? I mean, we will ignore the way that she does it, right? Because I mean, we know of a few ways already, as discussed in like the lectures and the homework, right? You do the teleportation, you entangle, you send over, whatever. But now the problem is now maybe there's some noise and Bob receive a different state, psi prime, right? So we have to ask a few questions, namely, I mean, because this is different from the classical setting, right? So in the classical setting, what did we see? We saw that this type of error can occur only, which is a bit flip, right? But in the quantum setting, you're not really sending over just a bunch of zeros and ones, right? Like now you can send over, the difference is that you can send over mixed signals, right? Instead of sending 0 and 1, you can send a superposition of the 0 and 1 qubit, right? So you can literally send a superposition. So now you have to deal with more errors, right? So the difference is the types of errors that you have to deal with, right? I mean, at this point, it's still unclear to us, right? Whether or not bit flips are the only type of errors, and it won't, right? Because one, you can easily have a phase flip, but is bit flip and phase flip the only type of errors? We will see. We will see. The other issue is that now you, instead of having the repetition code available to us, you can't, at least simply can't just say like psi, then send over like psi tensor with psi multiple times, right? Because I mean, there's this thing called the no cloning theorem that says you can't just go and clone a arbitrary quantum state, right? So it'll be a bit difficult, right? And these are things that we have to deal with strategically in order to send over a quantum state. Right. So I guess at this point it's useful to mention how the rough direction we are going with, right? This is different from, let's say, like other presentations that maybe they give a classical problem with some you use some quantum algorithm and you get like drastically faster results. This really isn't it. This is a problem about sending over a quantum state, right? And perhaps the key to understanding, at least for me, when I was reading the paper by Shaw and the relevant chapters in the textbook, the key to understanding how this worked for me was to understand properly how linear codes work. Cause I didn't really have the background, so I'll be spending some time covering this. So that will be the way we can understand this. So how will we model this scenario, right? In the classical setting, what did we have? We had a bunch of at least had a bunch of zeros and ones, right? So how can we just describe this properly? I mean, we can just, so Alice had some element u in the set of k bit strings, right? Uh, let's let's just, for ease of discussion, let's just say these are the k bit strings, right? Then what did she do? She did something to it, like she encoded it or something, and then you add some redundancy, right? And then you emerge with this bit string that you send over the noisy channel. And how do we say the errors can happen, right? You can have bit flips. But how can we easily model bit flips? It's quite simple, right? You just denote which position, which entry of the vector you want to have the bit flip, and then you just bitwise sort with 1, right? So you can have, maybe at the end of the day, after the noise, you will get this x prime, which is just x, and like entry wise you addition mod 2 with the error vector, right? So this is it's just a error. It just represents the error, right? And then what happens? Bob receives this X prime, and then he again does something with it. And the hope, right, is that of course Bob emerges with the same vector that Alice intended to send, right? The same bit string. And this will how we'll be looking at it in the quantum setting as well. You have some state psi, you do something with it, right? And then after that, you have this, you send it over after some noise, you emerge with the state psi prime, then you do something with it again, right? And then the hope is that you can get back psi, right? It's roughly the same idea. It's essentially if you thought that the solution, the way to model it in the quantum setting is just you add a q before everything, right? Bit you add q bit, at least you bought add q at least. It's the same idea, right? Okay, so now we want to look at these individual things here. And basically, as I said, the idea is I want to understand linear codes, at least enough to tell me or to give me some inspiration for how my quantum code will look like, right? So, okay, before this, I mean, we just need to get everything out of the way and talk about the things we need to discuss it, right? So first is this idea of uh the set of binary strings as a metric space, right? Because you want to be able to tell, like given some word, you want to be able to tell whether that is actually near to the code word that the other party intended to send over, right? So we can define a distance function over the code words, right? Called the Hamming, or sometimes called the edit distance, right? So how do we define it? We let V be some finite dimensional vector space. In our example, or for the purpose of discussion, we are just considering the vector space of n bit strings, right? Which will we denote like that. And so the Hamming distance between the two vectors is defined as this, right? You look entry-wise, right? Because you're running over all the entries. You look entry-wise, where do they differ? And you sum up the value of the indicator function. What does this mean? It means, let's say I have this 0, 0, 0, 0, right? And I have some vector 0, 0, 0, 1. I want to see how different they are. What do? I look entry-wise, right? Hey, this guy is the same as this guy. This guy is the same as this guy. This guy is the same as this guy. Wait, they are different. And I have there, so you know that they are one away, right? The distance of one, right? And you can do the same for others, right? Like let's say you have 1, 1, 1, 1. You would think that this is further from this than this is, right? And you'd be right, because the distance here is 3, distance here is 4, right? So already you kind of know that this sort of follows your idea of what a distance should be. Now, it's useful to define the idea of a minimum distance of the code, right? So what does this mean? Basically what the minimum distance is you take this Hamming distance, you use it to compare pairwise between each of the words in the code, right? So your code is like this is it's a subset of all these bit strings, right? So you look at this set of bit strings inside the code, then you compare the distance between each of them, you take the smallest possible one. So what you have is, if the code has a minimum distance of this, what does this tell you? It tells you that I know given any x or x prime in C, they are at least the minimum distance apart, right? They are at least d min apart, and this will help us later on when we talk about, how can we decode things, right? So yeah, now the question is, how many wrongs can we write, right? So first to get this out of the way, yes, the Hamming distance, right, that we discussed earlier, it obeys all the properties of a metric. So the set of bit strings together with the Hamming distance together form a metric space. What does that mean? It means that we can talk about distance, we can consider them, all the words, as points on some space, and we can have an idea of distance between them, and it follows everything, right? Like it follows the triangle inequality, and the distance between itself and itself is zero and stuff like that, right? And it also conveniently uh allows us to have this proposition, right? A code C with minimum distance D can correct up to D minus 1 over 2 errors. How do we see this, right? I mean, uh, so what does it tell you? Okay, let me give the rough idea. The rough idea is this. You have, and we all experience this, right? Your friend sends you some message. Your friend says, I'm on my way, right? Your friend says on my way, but there's a typo, and then your friend sends you like on my way or something. And I mean, you look at this, you can sort of tell that they meant on my way because they only differ by this one alphabet. And you look at your keyboard, A is kind of near E. So you know, if your friend doesn't make too many mistakes when typing, you can sort of infer what your friend originally wanted to tell you, right? So if your friend didn't make a certain amount of mistakes, you can infer back what your friend wanted to say. I mean, contrast this if your friend send like on my, like, I don't know, your friend send on my AXN or something like that. No way you can tell your friend wanted to say on my way, right? Or maybe if your friend said send you like and my AXN, what is your friend even saying, right? So the idea is that you can tolerate up to a certain amount of error, right? And still be able to recover back your original code. How much error can you tolerate? Well, this proposition tells us precisely is this amount, d minus 1 over 2. Where this d is the d min of the code, right? So the way we can see this, I'll just give the rough idea of the proof. I mean, of course, we are in a metric space, right? So we have the irresistible urge to play with balls, right? So we have this x1. So suppose we have this, we are dealing with a code C, and we have a bunch of code words inside, right? X1, X2, maybe they are scattered around like this. We know that because the minimum distance is at most D, right? At least D. So we know that all these guys will be at least D apart from each other, right? The distance between all these points are at least D apart. And we know that because there's up to D minus 1 over 2 errors, right? We can draw, okay, and we'll just like call this T. We can draw T balls around each of the points, right? So we know that the purpose is this, right? We know that if there's at most T errors, right, your original word that you intended to send, let's say x3, will get displaced to somewhere within the t-ball of x3, right? So maybe you get sent here, you get sent here, a bit gets flipped, you send somewhere nearer. You know that either way, you remain in the t-ball of the word that you originally intended to send. So if I'm the recipient, all I need to do is when I receive a word, I say, okay, what is the center of the t-ball that like this guy belongs to, right? Like whose ball this guy belongs to, right? So I I mean, let's say I get this guy, I just say, oh, who does he belong to? Okay, he belongs to this guy, right? X3. So I know that I mean, sorry, you get this, wait, sorry, you get this word, right? You look who, because you know that I will definitely be in some ball, and because my T is chosen this way, I know that all these balls don't overlap. So I know that I'll be in at most one ball of a valid code word. So all I need to do is to know what valid code word that was intended to be sent over. I just need to look at the center of the ball and I will know. Okay, so that is the rough idea of why a code with minimum distance d can correct up to d minus 1 over 2 of errors. Okay, so let's go back to the setting we were discussing previously. Right, so previously we said that we had some k-bit string u, and then we did something to it. We added redundancy, we added some parity checks or whatever, and then we got this n-bit string n. And then we sent it through the noisy channel, and there was some error vector e that you bitwise saw with it. And then the hope is that when Bob receives this thing with the error, he's able to do something, and hopefully at the end of the day, he will get back you, right? So now let's look at it piece by piece, right? So let's look at this first piece first. So what exactly is going on here, right? There's some k-bit string u and it's getting mapped to n-bit string, right? So we can kind of view this as just applying some matrix G on the vector u, right? So we will get that our code will just be G, we feed u into the generator matrix G, right? So consequently, we will just call this a generator matrix, right? So what is this? Is just the generator matrix is just an m by k matrix whose entries are just either 1 or 0. And its image, since we are using it to generate all the code words, right? So its image must be the set of code words, right? In other words, the columns must span C, right? So let's take a look at some examples. So consider the repetition code, right? You have 2 bits, you just repeat them 3 times. What will the generator matrix look like? So let's say I have some original message 1 0. What I want to get is g of u is, maybe we write it as a column vector 1 1 1 0 0 0, right? So what would the generator matrix here be? It's quite simple, right? You just do something like this. You have 1 1 1 0 0 0 0 0 0 1 1 1. right? So you can see when you multiply any vector with it, like let's say 1 0, excuse me for multiplying it this way, but you see that you will get 1 1 1 0 0 0, right? Whatever it is, the second one will get repeated 3 times because of this guy, and the first one will get repeated 3 times because of this. So this will be this is an example of a generator matrix for the repetition code. Right. So moving back to our this picture, right? That was the first part of the picture. The first part of the picture, we saw that there was a generator matrix that takes the vector u to one of the code words, right? Now let's focus on the next part, the what over here. We have we have this error that is bitwise sort with the vector that we want to send the code word. And now Bob has the task of somehow deciphering what was it that Alice had meant to say, right? And he can do this with what is called a parity check matrix. So he does, like, let's say parity check. And he doesn't directly get U, but he gets let's call this parity check H, right? So H goes from n bit string to a n minus k bit string, right? So Bob will get this thing called h of x prime, which is called the syndrome, right? Which basically it helps you diagnose where did it go wrong, right? Where did the message go wrong? So because of this, we can say that so about the parity check matrix, and we will see an example shortly. So the parity check matrix is just n minus k by n matrix, which tells you where basically where is the problem. So what you want is that, I mean, if there's no problem, and if you are doing when you are multiplying, so let's say x prime actually equals to x, then we want that h of x equals to 0, right? Sorry, h of x prime equals to 0. Meaning to say, the kernel of this h is the set of code words, right? So when there's no error, we always get the 0 vector back after feeding it to the parity check matrix. Consequently, for any linear code with parity check matrices H and G, we have the HG equals 0, right? Since G is the image of G is in the kernel of H. So everything that G spits out will get killed by this H, right? And this actually helps us in when we have this syndrome, right? Because this syndrome will become extremely useful in telling us where did things go wrong, right? So how it works is that we know that since the kernel of H equals C, we know that we are able to, we know that our x prime error, our x prime, the message that Bob receives is this, right? X plus E. And we know that this part will get killed by H, right? Because it lies in the kernel of H. So what happens is that when we take H and we multiply by x prime, what we get is this, right? And by linearity, we can separate these guys out. This guy will get killed, and we are left with this. And this is the syndrome, right? And this will be the vector that will tell you perhaps which position is it that the error had occurred. So we can take a look at this simple example called the Hamming code, right? So this is its definition. Suppose r greater than 2 is an integer and h is the matrix except for the zero vector is all the other bit strings of length r, right? So it defines a linear code. And the nice property about this Hamming code, right, is that the relation between the syndrome and how to decode it is very explicit. The syndrome tells you exactly which bit got flipped. So and see that we only need to define H here, right? Because it's actually sufficient to define the parity check matrix only. Because H will tell us what the set of code words are, right? Because recall that the C is in the kernel, C is the kernel of H, right? And then so to find G, we just need to, pick a set of vectors that span the kernel of H, right? So to find G, right, and we can actually show that this Hamming code actually only can correct a single bit flip. So, okay, but that was not the main focus. We just need to let's just run through an easy example, right? So suppose we want to consider a 743 Hamming code. And I think it's worth mentioning now that the way we normally we talk about the codes is this is N, this is K, and this is D. Where N is the length of the code, and this is the length of the message you want to send. And D is just the D min that we talked about previously, right? The minimum distance between each of the code words. So you can see that because this is a 743 Hamming code, recall that it can correct up to D minus 1 over 2 errors, right? In this case, well, there is just one. It can correct a single bit flip. So recall the definition of the Hamming code, right? It's just all the bit strings. The parity check matrix is just all the bit strings that are not the 0, 1, right? So we can write H equals to this guy, right? So I'm just gonna list out all the bit strings here. Right, and from there, how do we can find G? We just need to look at what lies in the kernel. And of course, I've already secretly done this, right? Or secretly looked it up. But on top, we just have the identity. Now, let's try to see an example of how this whole process works, right? So at first, remember, we have some U, right? We have some U, then we want to apply G on U, then to get X, right? So let's do that. Let's say for example, U is 1101, right? So we take U, we apply it, so we multiply here, 1101. What do we get? So we can work this out. We can see that the first four rows is just the identity, so we'll get back 1101. Then after that, we just compare, right? You get 0, 0, and 1. So this is no longer G, this is G of U, right? Now suppose we have E equals 0, 0, 0, 0, 0, 0, 1, right? Meaning that only the last bit is flipped. So what will happen to this guy? This guy will become a 0, right? And let's just take this away. So now our error vector x prime is this. Sorry, our message that has been corrupted is this. So what do? We feed it to the parity check matrix, right? So now we just need to calculate h times x prime, right? And recall that that just gives us the syndrome he. Since the original x will get killed by h, right? So what do we get? Well, we can do the multiplication and we'll get 1, 1, 1, right? Which happens to be 7 in binary, right? And this is no accident, this is by design. So that actually we can see that the error actually, sorry, the syndrome actually tells us exactly which bit got flipped. Because remember here, it's a 7th bit, right, that got flipped. So now we know what to do, right? All we need to do, take this guy, change it back to a 1, and call it a day. So let's talk about dual code. So a dual code for NK code C, what happens is just we take the transpose of the parity matrix check matrix as the generator and the transpose of the generator matrix as the parity check. So we say that code C is weakly self-dual if C is a subset of C perp, and strictly self-dual if C equals C perp, right? And let's look at another way of talking about this, right? So we can say it's weakly self-dual if the transpose of the generator matrix multiplied by a generator matrix is 0. So let's try to give roughly the justification for this, right? So suppose the code is weakly self-dual. So what does that mean? It means that C is a subset of C perp, right? Since C is a subset of C perp, we know that C is a subset of what is another way of describing C perp? Well, it is the kernel of its parity check matrix, right? So C is inside the kernel of G transpose. Then for all of the U, that in the set of k-bit strings, we have that G transpose G U is G transpose X, where X is in C, right? Equals 0. So we have that G transpose G is 0. Right? And the other side is roughly the same argument, right? If G transpose is 0, then C is in the kernel of G transpose. Then C is a subset of C perp. Right? So moving on, this is something about the dual code that will be a bit more useful. So if C is a linear code, if X is in C perp, then we have this sum to be equal to the cardinality of C. But if it's not, it's equal to 0. How do we see this? Well, let's first consider the two cases, right? If X is in C perp, then what happens? We know that X dot Y equals 0, right? So that sum just becomes this, which just becomes the cardinality of C. But if X is not in C perp, Then for this what happens? Well, this is taken over all of the possible codes in C, right? So what happens? We have an equal probability of this dot product becoming half and an equal probability of this dot product becoming, we have with probability half, we have that this x dot y equals 1. With probability half, we also have this x dot y equals 0. So this whole thing equals 0. Since the probability of this is half, and the probability of this happening is also half, right? And let's just keep this in mind because this will be something that is very important in our CSS codes. Okay, so now we are ready to understand CSS codes. So what we do is we take two linear codes with the following properties. They are NK1 and NK2 codes respectively, such that these hold, right? Then after that, we define this coset as the following superposition, right? And so what we see is that it becomes an equivalence relation, right? Where the two qubit, the code words are equal if their original code words are in the same coset. And how many cosets do we have? Well, we can count, right? We can count the number of cosets in this quotient. We just divide them by the cardinalities, right? Based on the Lagrange theorem or something. Then we get that there'll be this many cosets, and therefore we can map this many, we send over this many bits. Okay, so given this code word that we send over, what can go wrong? Well, I claim that it's sufficient to just consider bit flips and phase flips. Why? We showed in assignment 1 that we can write any 2 by 2 complex matrix as a linear combination of the poly matrices along with the identity, right? Furthermore, we know that we can write Y as this, right? I times XZ. So actually, whatever error that is applied on whatever error that's applied on the following state above is just actually a bunch of either bit flips or phase flips, right? So at the end of the day, it is sufficient to just consider bit flips and phase flips. And this is good, right? Because we we know exactly how to do and undo them easily. So specifically, we suppose that if the bit flips were described by the error vector E1 and the phase flips were described by the error vector E2, if this was the original state, then the new corrupted state is this, right? Maybe let's not include this. This is not really right. So this is the new corrupted state. Now, from this corrupted state, it's not entirely clear what to do, right? First of all, we shouldn't exactly measure it, right? Because if we measure it, we will collapse it to any one of the states in the superposition, right? And then we cannot recover the actual state. So measuring is kind of out of the question. So we have to find some way to find the syndrome of any of the errors, so-called without like directly measuring it. So how can we do that? Well, recall that the codewords of C1 lie in the kernel of the parity check matrix. So what we can do is that we can find some circuit that will map, let's say the vector, sorry, the cat, this along with some ancillas over to the following state. Right, so we find some circuit that can apply the parity check matrix to the state that we have with the error, right? Then, since C1 lies in the kernel of the parity check matrix, this will actually just become the syndrome, right? So once we have the syndrome, we can easily correct the errors just by applying the appropriate number of like poly x's in the correct places. So what we can do is, and I won't go in detail on how to construct the circuit for this, but we can use a bunch of C dot gates to compute the above transformation, right? So after this, we will have the state this, we will have the same state as above, right? But the advantage is now that we know the error syndrome, so we can calculate the what exactly what bit flips we have to do to recover back the original state. So once we have corrected for the big flips, we have the following state. Right, this is after we correct for the bit flips. Now the question is, we already know, at least from the above, right? Okay, pretend that we knew exactly how to use the C knots to compute the parity check matrix, which we can, right? Suppose we know this, we have this in our hand already. Then now this how do we correct the phase errors? Well, what we can think of it as phase errors are just bit flip errors in another basis, right? So as with all quantum algorithms, we just do Hadamard, right? So so that we can change the phase errors to bit flip errors. So the solution is just to apply the Hadamard gate. After that, once we apply the Hadamard, we have the following state. Where is it in C2 plot? So now, if we can rewrite this sum, right? So if we let z prime equals z plus e2, what do we have? Well, remember that we showed in the previous exercise that if we have z, okay, let's first rewrite it. So then we have the following state. This is now z prime, and this is z prime plus e2. Now we see, right? Nice, nice, we have this here. We have to try to somehow uh massage this expression so that we can make it similar to this, right? And once it's similar to this expression, we already know the solution. Use a bunch of C naughts to compute the syndrome and just do the according bit flips, right? Well, we showed above that if Z prime is in C2 perp, then we have that this whole thing becomes just the sum becomes just mod C2, right? This was something that we showed before. And if it's not, then well, the sum goes to 0, right? So now we can take this expression and we can finally rewrite it in the form that we want. And now this looks very, very similar to the state with the bit flip error, right? So what can we do? We can do the same thing as we did before, right? We just do the same computation and then we calculate the syndrome. So we compute the syndrome. Then we apply the poly axis in the correct places, right? So after that, well, we just get the corrected state. And now we have successfully fixed all the phase errors, right? So what's left is just to change the, since to solve the phase errors, we change the basis, right? Now we just change back. So we just apply the Hadamard again, and then we recover back the state that we originally wanted. So just to recap what we did, right? We said that it was sufficient just to consider bit flips and phase flips. So from this original state, we get this, right? Where this is the phase error and this is the bit flip. And we know that we can't really measure it because then we will just collapse it to one state and it's game over already. So we have to try to find a way to compute the syndrome without actually measuring it. And what we did is we just added a bunch of NCLAs, computed a syndrome using a bunch of C naughts to do the parity check matrix. And since this guy, like in the kernel of the parity check matrix, well, then the output will just become the syndrome, right? And then we just corrected for the errors just by applying poly access. Now, the idea to fix the phase errors was to just apply the Hadamard. And then now it reduces to the bit flip case where we can just apply the same procedure as we did above, right? And then we just apply the Hadamard back and we get back our original state. Okay, so now we can talk about the Gilbert-Vashamov bound. Right, so it basically says that as n become large, there still exists error correcting codes on that can protect up to t bits, such that this inequality holds. Right, so how did they establish this argument? Well, it's through a greedy argument. The rough idea is you can estimate, right? Remember that to correct certain errors, we have to maintain a minimum Hamming distance between them, right? So let's say you have this code word and you can try to fit more and more and more code words, right? So a code is kind of good when you fit as much as you can, and it's bad if there's still some space. Well, what you show is that, like, let's say the probability of a bad code word is less than one. So the argument establishes that the probability of the bad code word is strictly less than one. Therefore, there exists a good code word where, a good code where all the you pack in as many code words as possible, right? So this is a non-constructive proof, right? Namely, it doesn't tell you what the code looks like, uh, yeah, how to correct the errors, what's the syndrome, all that. It just gives you the existence, right? Then it's about a skill issue whether or not you can find it. Same deal for the quantum Gilbert-Varshamov bound, right? The argument is a bit complicated, but basically the idea is also the same thing. You apply some greedy strategy, but using the CSS codes, you can make some argument that to show that this is true. Uh, this, frankly speaking, is outside the scope of this presentation. If not, it will be a very long discussion. But so yeah, so this basically establishes the existence of good quantum correcting codes, error correcting codes, right? Similar to the above. And that's why it was important to understand the CSS codes, because the idea of like the weakly self-dual code and all that was used in this argument, right? So as n becomes large, there exists a code as long as you're willing to pay this trade-off between the rate and the amount of codes that the amount of bits you can protect, then you have such a code does exist. So now let's do a recap. What did we do? We went through the basics of linear codes. Namely, if you remember, we talked about Hamming distance and what conditions such that you can correct the errors on a number of bits. We discussed the generator matrix and the parity check matrix, right? And we also gave some examples of the Hamming code, right? Namely, we showed that the Hamming code is nice in that the syndrome tells us precisely the position of the bit that got flipped. Then we also showed how we can use linear codes to construct and their duals to construct CSS codes, right? Namely, we also argued that it's sufficient to consider bit flip and phase flips, and that if you want to correct the phase flip, you just do a harder mark and change it to the problem of the bit flip. Then use a bunch of CNOTs, find out the syndrome, and just do the corresponding poly access. Finally, we ended off by discussing the existence of good quantum error correcting codes as given by the Gilbert-Varshamov bound. Okay, That is it for today. I hope you guys enjoyed my presentation. Thank you.